Hello, my name is Steve, and welcome to part 2 of my exploration of basic programming for the Atari 2600. In part 1, we reviewed using this cartridge to write programs, including the use of the keyboard controllers for input. We also discussed many of the limitations to the language implementation, including the restricted amount of usable RAM presented by the hardware. Be sure to watch that video if you haven't already. It's linked in the description below. In this video, we'll conclude with the overview of the music, keypad input, and graphic features, as well as some optimization techniques to minimize the amount of memory that your programs use. Let's continue where we left off in part 1. Okay, these next short programs will demonstrate the music and keypad inputs of the basic programming environment. So this program uses the note variable, and when you assign an integer value to the note variable, it will play a particular note on the B scale. So from values 0 to 7, you'll get the full range of the scale, and any values greater than 7 are just going to be the modulus of 8 applied to that, and it will correspond to the note on the scale accordingly. So when we run this program, we should hear the scale repeat indefinitely. Oops. Okay, enough of that. Now, as note approaches the maximum integer value of 99, then you're going to have a scale problem, especially if you just wanted to write a program that plays the B scale forever. So let's demonstrate what happens when you have overflow in this particular program. We'll set this to, say, 88, and we will then reset the state of the program with reset, and let's play this again. And there you have it. So to fix that, it's pretty easy. All we need to do is put a mod 8 operation when we manipulate note, and then we'll always be guaranteed that whatever value note has, it's going to fall cleanly on the B scale. And we can run this again, reset my state, away we go. Okay, so now let's make a little program that takes a keypad input and plays a note whenever you press one of these keys over here. We're going to be using the key function or the key variable for these next few programs, and I'll write a really quick program to demonstrate what this does because it only reads input from the second keypad controller, and some of these buttons don't nicely map to the integers that you would expect to see when you press the keys in numerical order. Okay, I've started running this program, and you can see when no keys are pressed, the value that's returned by the key function is 0. And I can start pressing keys on this keypad, and you can see that they increment nicely from 1 all the way through 9. When I press this one, I get 99, or -1, or however that's interpreted internally. This one here returns 1, surprisingly. And this one over here is 0. Okay, so that's what happens with the key function. Now let's map that to a little musical program which I call the Atari Piano. So this program checks that the value of the keypad input is between 1 and 8. So specifically from this key button to this key button. And that maps nicely to the note function because the note takes values from 0 to 7. So all we have to do is subtract 1 from whatever we've pressed, and we effectively have a piano on the B scale from B and 1 octave higher to B. This program is adopted from a very similar one in the basic programming manual, and it has a small problem with it, which you've probably spotted already. Let's see what happens when we run it. Okay, I'm going to start pressing some keys. Let's press the 2. You can see that sometimes it plays a weird 99 note. How does it get 99? Well, let's slow it down and let's see what is happening a little bit closer. So I'm going to press the 1 note again. There we go. Let's slow it down a little bit more. Did you see what happened? There's a race condition in this program. We are constantly evaluating the key function at different points in the program's execution. So we could potentially get past the if statement that checks to make sure we're a valid key, and then release your hand from the key, and then it will play an invalid note when it attempts to evaluate the expression that is assigned to the note function. It's quite amazing that there's a race condition in a sample program from the basic programming manual. But I think it's intentional, because if you skip ahead to the last few pages of the manual, they provide an almost identical program that corrects the problem. Okay, so in this program, what we're now doing is we're assigning the key input to a variable. And then what we do is we do all of our checks for validity of that key input on the variable. So the keypad input is only evaluated once per execution of the loop. That way, there's no race condition. We always know what the value was at that moment in time, and then we can play the note accordingly. Okay, and now with that, you can play whatever musical tune you can conjure, as long as you can map it nicely to the B scale. All right, the last set of features to explore are the graphics features, and those come to us with the HOR1, VER1, HOR2, VER2 special variables, and the hit function. These control the horizontal and vertical position of one block on the screen, and these control the horizontal and vertical positions of the other block on the screen. The hit function determines if the two blocks that are visible in the graphics area are overlapping. Let's demonstrate that with a quick program. For that, I'm going to disable the headings, and I'm going to enable the graphics section, which is this button. Okay. Okay, so this program basically increases the horizontal position of one of the blocks by 3, and then the vertical positions of the alternate block by 3 as well. And then we check to see if they're overlapping by executing the hit function and storing it in the variable called h. The variable screen, or the variable tab, should be open. It is, and we should see the values of those variables as we execute this program. So let's take a look. Okay, so we've incremented everything by 3. There's a little bit of overlap, so the hit function returns 1. Let's run it again. Okay, still a little bit of overlap. And of course, now that we've separated the two blocks, there is no overlap at all, and so the hit function returns 0. Now, this is the extent of the graphics functions that are available to you, so if you wanted to make a game out of them, it will take some imagination for interpreting what exactly is going on. Now, I don't have this level of creativity, so the next game I'm going to demonstrate is straight out of the programming manual for basic programming, and it is the Pong game. Let's take a look at that. Okay, I've done something a little strange here. I put a go-to1 on the last line before I've entered any of the rest of the program. And this is because this program will take up the entire screen, so we will not see that last line. And therefore, I wanted to enter it first and not have to worry about it later on. Alright, this program is a little complicated, but what it essentially does is allow you to move one of the two blocks across the top of the graphics area by inputting the amount of direction or the amount of distance to move from the second keyboard controller. That's the first line of code. The rest of the code basically manages the second block, which moves it towards the top diagonally. And if there's a collision between the first and second block, then the second block changes direction and moves back down towards the bottom of the graphics area. Now there's an interesting programming technique being used on line 4. You can see that we're assigning the value of ver1 to whatever it is plus the result of an if statement. And that's kind of weird because we generally don't think of an if statement as a function in conventional programming. But in this case, what's happening is that both the branches of the if statement result to an integer. So it doesn't matter what comes out, as long as we evaluate that if statement first, the entire expression, we get an integer result, then we can assign that to the ver1 variable and complete the expression. So I'm going to turn off the program section so that the graphics section is visible, and I'm going to run this program and we can see what it does. And let's speed it up. So the objective is to make a collision between the red and white blocks. I'm controlling the white block, and this is very cumbersome because I don't know where it's going to end up. And I can't go left. That's another problem. I can only go right if I fix the mount, and then once I get to the end of the screen, I'm going to wrap to the left side once again. So I'm going to park my block where I think the red one is going to go, and I'm going to try and get them to make contact with one another. There we go. And it bounces down this time. And this is Pong. This is the solitaire version of Pong using basic programming for the Atari 2600. So that will conclude a feature overview of all the keywords and programming language features that you have available to you from this basic programming cartridge. The last thing I want to show is a real-world scenario, of debugging and optimizing a program. And this came to be when I started entering a program that I saw in the basic programming manual. It's called a clock-like program or something to that effect. And basically what it does is it renders the minutes and seconds in a clock-like fashion as the program executes. And the problem that I had is I wanted it to show the hours as well. I figured that would be more of a clock-like program if you include hours. And I figured the reason why it wasn't included was because of the memory limitations of this cartridge. So let's start entering the program and we'll iteratively go through and improve it as we go along and hopefully get to a situation where we can render hours, minutes, and seconds accurately on the screen. This is the variant of the clock-like program from the Atari Basic Programming Manual. And effectively what it's doing is it's counting hours, minutes, and seconds. Well, in the opposite order. Second, minutes, and hours. And it does so by doing modular arithmetic each time one of the counters for seconds or minutes wraps around back to 0 again. And on every iteration of this loop, we're going to print the hours, minutes, and seconds to the screen, making sure to clear them so we're only using one row of screen memory. So let's see what happens when this program runs. I'm going to turn the program off. I'm going to put the status on, and I'm going to put the output on. And let's put the stack on as well. Okay, here we go. Okay, and the program stopped and it prints out some nonsense. What's happened here? Well, the program has run out of memory. We don't have enough memory to store the program and its variables, and also to pay for the stack and variable section of the screen. In fact, the output is pretty messed up and the variables section is pretty messed up, presumably because there's 0 symbols left or 0 RAM left for the program to do anything useful. So what can we do to make this program a little bit better? Let's go back to the program listing. First, I'll reset so that we get our memory back. I will keep the status off. I will turn the stack off, the variables output, put the program back on. So if we remember from a previous sample program, I noted that you don't need to print stuff to the screen if all you're doing is tracking numbers and variables specifically, because you're already paying to do that in terms of memory. Basic programming is going to keep track of that in the variable section. So what we can do is we can go forward to line 4 and we can remove it completely if we're comfortable with using the variable section as the program's output. And that's perfectly fine for a program like this. So we'll go ahead and remove it. Okay, that's going to save us approximately 10 bytes or so. I don't know how much it is. We'll go back to the status screen. We'll turn the stack back on and we'll turn the variable section on. And if we run the program this time, make sure I reset, then what will happen is we have a program that's running and it's going to increase this count indefinitely. Now it looks pretty safe that this program will not run out of memory, even though it's going to have to print an extra minutes row and an extra hours row in the variable section. That's going to cost us at most 8 bytes, roughly 8 bytes of memory, maybe 9 or so, depending on if there's any line feed characters it has to track. But if you look at the current symbol usage, it's kind of hovering around between maybe 15 to 17. And so it looks pretty safe that this will run indefinitely. But there's one problem with this program, and is that clocks don't always start at 0. We might want to initialize them to a certain time. So let's see if we can put some initialization logic into the program and figure out what that's going to do to the memory consumption. So let's add a line to the beginning of the program that sets the hours and minutes. I'm not concerned about the seconds. Okay, so this sets the time to 17:59 or 5:59 p.m. And I did that intentionally because I want to see what happens when the seconds roll over and increment all the other variables. So let's disable, or let's reset. Let's disable the program. Let's enable the stack and the variable output and the status. And let's see what happens. Oh, another crash. Well, what's happened here? We ran out of memory before the program could do anything useful. And it looks like those 2 variable initialization statements really botch things up. So there's a nice trick you can do to get around this. I'm going to reset the program. I'm going to turn the program on. And I'm going to step through this one statement at a time to initialize the clock. You can see the symbol usage going down based on what's happening in the stack and in the variable sections of the screen. Okay, and there's where we had 1 symbol left and obviously now it can't run the next line. But now I'm going to do something really sneaky. I'm going to go back, because my program memory is still intact, I'm going to go back and erase this first line, because I don't need it anymore once the initialization has happened. So I can erase all of this, I can get my memory back, and if I turn the program state off now, you can see that the hours and the minutes have been initialized in the variable section. And I think this will let my program run through completion. And away it goes. So that fixes the problem, but clearly that's not an ideal solution. Clocks don't work like that in real life. You can't just move some instructions around because you didn't set the time properly and then hope that things will work. So let's see if there's a better way to fix this. Okay, so I've reset the program state and I've gone ahead and re-entered that initialization line. Now if we look at this program, we can see that there's a bit of duplication between lines 3 and 4. Oops. For example, there is an if statement that checks if the seconds are 0, and then it increments the minute counter mod 60, and then in the next line following, there's the same if statement that checks if the seconds are 0 and the minutes are 0 before it increments the hour counter. When I did a bit of experimenting, I realized that I could just remove this one if s equals 0 statement and collapse the remaining expression on the previous line as follows. And this shows an interesting caveat of the if statement, which is probably the most interesting statement in this entire programming environment. So what happens here is that everything after the first then clause is considered the first branch of the if statement. So on line 3, if s is equal to 0, then increment m by 1 mod 60 and execute the following statement, which is the next if statement. If the minutes are 0, then increment h by 1 mod 24. So if s is never 0, then we never execute any of the following statements on line 3. And that is great because that saves us approximately 7 symbols or 7 bytes of memory for our program. And let's see if that has any impact on the execution. Oops, I went ahead and started running and explaining what was going on when I forgot that I have to change this last goto statement to now goto 2, since we don't want to reinitialize the clock every single time. So that will be edited out, and now I can explain what's happening. So what's going to happen when we run this program? Are we going to consume additional memory? Is it going to crash? Let's find out. And let's run. And it seems to work just fine. What happens when s gets to 10? No crash. We're still within the memory limitations of available memory. And if you pay close attention, you'll notice that the program is running a lot faster in terms of the amount of time it takes to increment 1 second. And the reason for that is because we don't have this if statement on line 4 that we have to evaluate every single time in our loop. And that is a wrap. I hope you enjoyed watching and learning about this fascinating basic programming language implementation. While working on this presentation, I was particularly impressed with what Warren Robinett accomplished with only 4 kilobytes of instruction code and less than 128 bytes of RAM. When compared with the basic programming language offerings of other microcomputers in the era, we can't deny that basic programming is very limited. But at the same time, we get a peek at some rudimentary music and graphics features and also have access to a near complete debugger. Yes, a debugger for the Atari 2600. While inputting programs, I felt the frustration in trying to do anything useful with this cartridge. However, my background in computer science allowed me to put that frustration aside and focus on working within the limitations. I don't think that others without this experience could do the same, especially a young child who only had an Atari 2600 to experience computer programming. The environment is basically a basic version of BASIC, and a more elaborate microcomputer is needed to do any practical learning. Thank you for your time and attention, and I hope to see you back soon.